Hello, today I'm introducing the latest release of OSM from Endace. OSM is a security hardened operating system that runs on every Endace appliance. OSM includes graphical and command line user interfaces for administration, management and performing investigations. Our latest release is OSM 6.5, which introduces a new architecture for managing large fabrics of Endace appliances and for centralized investigations that may involve more than one appliance. We've also refined our search algorithms, which can yield amazing speed improvements when searching across large and potentially distributed data sources. In this video, I start off by overviewing how Endace CMS and a new software component called InvestigationManager are used to administrate and perform investigations over a globally distributed fabric of Endace probes. I then go on to show how InvestigationManager works to perform investigations across multiple appliances. As part of this, I cover how Endace probes can be combined into stacks to create a logical Endace probe of higher capacity. Then I talk about improvements to our search algorithms, which really benefits the productivity of analysts involved in threat hunting. In the remainder of the video, I demonstrate InvestigationManager being used in a real-world threat hunting scenario. This includes demoing a search over 1.3 petabytes of globally distributed packet data that takes just 30 seconds. Okay, so let's get into it. Here, we're showing a globally distributed fabric of Endace appliances. To illustrate the concept, we're just showing a handful of physical Endace probes, but in practice we have customers with much larger fabrics than this, counted in hundreds and even into the thousands of appliances. You'll see that in some locations there's one Endace probe, and in some other locations there's a stack of probes. I'll talk about that more in a moment. Those of you familiar with earlier releases of OSM would recognise Endace CMS. Endace CMS is used by the operations and/or IT staff responsible for administration and management of the fabric. It lets you centrally manage the entire fabric, things like user account management and pushing out software upgrades and appliance configurations. Now this is where we've made a change. Previously Endace CMS was also used for centralized investigations. In OSM 6.5 we've extracted this functionality out of Endace CMS into a new standalone software component called InvestigationManager. InvestigationManager is designed for performing centralized investigations across one or more appliances from a single pane of glass. The user interface for performing investigations and searches is almost identical to what you'd find on an individual Endace probe, with the major difference being that you can select data sources from more than one appliance. So InvestigationManager can be used for investigations and searches involving just one probe, a group of probes, or even every probe in the fabric simultaneously. In many cases, multiple instances of InvestigationManager will be deployed to partition investigations by regions, networks, and/or job functions. For example, here we're showing a global fabric partitioned into 3 regions, and within each region, NetOps, DevOps and SecOps have each been allocated a dedicated instance of InvestigationManager. So let's have a closer look at how InvestigationManager works to perform investigations across multiple appliances. I'll use an example of a stack of probes. Stacks are used to effectively create a logical probe with greater capacity, and by capacity I mean the ability to scale both storage depth and packet capture rate. So you can build a stack to capture at full line rate on say a 100 gigabit Ethernet link, and or to have enough storage to keep say 6 months of network history. How does it work? Well, you use a network packet broker to distribute the monitored traffic across the probes in the stack, and then you use InvestigationManager to perform investigations covering probes in that stack. Reach out to your local Endace representative who can provide you all you need to know about building stacks. Okay, let's have a look at how InvestigationManager works by showing an analyst, maybe from the SecOps team, performing an investigation involving the 4 Endace probes in this stack. So the analyst initiates a search using InvestigationManager, which then coordinates this search across the 4 Endace probes. InvestigationManager doesn't perform the search itself, it initiates the searches on each of the probes. These searches then happen concurrently, with each probe sending results back to InvestigationManager, which by the way, presents results as they come in rather than waiting for every probe to complete. This is a highly distributed and parallel architecture. It scales horizontally, so on average it won't take any longer to perform an investigation over 40 probes than it would over 4. We've also refined our search algorithms in OSM 6.5, which has seen some amazing reductions in search times for needle in the haystack scenarios. That's where you're searching for just one or a small number of instances of a specific IP address, an IP port combo, or an IP port protocol combo. So let me show you a demo of it in action. In this scenario, a multinational company has a fabric of Endace probes scattered around the world to record traffic at key points throughout their network. Their security system has flagged that on the 15th of December, a PC on their network downloaded an exe file from the internet, and a short time later that PC uploaded around 20 meg via an HTTP post. That PC is at 10.1.2.1. This could just be an employee uploading pictures to a web service, or it could be something more sinister. The logs from the security system don't have enough detail to know. Fortunately, the packets should have been recorded because the company has provisioned their fabric of probes to maintain around a month of network history. The traffic could have traversed through one of several gateways to the public internet, but to save time figuring out which, we'll just use InvestigationManager to search all probes that might have captured the traffic. In this case, that's 7 probes, a couple of individual probes, and a couple of small stacks. Okay, this is InvestigationManager, and here we can see the 7 Endace probes that have been connected to it. By the way, this InvestigationManager instance is running on a server in North America, whereas I'm sitting in Asia Pacific, and these 7 probes are distributed across both those regions. So this is a truly authentic demo of a globally distributed investigation. Everything's showing green, so we're good to go. I'll create a new investigation that uses all the connected probes as data sources. I do that by selecting a tag denoting all rotation files. There we go, 7 data sources. Now we know that the security system flagged the anomalous activity on the 15th of December, which is about a week ago. So let's search everything from the 15th of December right up until the present, because this might reveal more recent activity. We'll start off by looking at the traffic breakdown. So it's now building out a breakdown of all traffic across that data range. Now with the massive amount of data involved, this takes 1 to 2 minutes to complete and isn't really going to help much because the vast majority of that traffic is not relevant to this investigation. However, one thing it does give you is how much packet data we've just selected. Again, knowing that isn't really going to help you in individual investigations, but in this instance I do want to show you just how much packet data we're dealing with. So here's one I prepared a few minutes ago. By looking at the traffic breakdown, you can see that over the week or so time period that we're interested in, there's just over 1.3 petabytes of data spread across the 7 probes. Now we have to search all of that data to find just the traffic related to our potentially compromised PC at 10.1.2.1. The good thing is you don't have to wait until these tools finish if you don't need them to, so we'll go ahead and search for all packets associated with this machine. So that you'll be able to see how long it takes to search for these packets of interest, I'm going to start a timer when I press apply. Okay, and now it's searching for those packets of interest. We can see already that it's found some traffic, some hypertext, some Microsoft, some SSL and DNS. By the way, you can hide and show those individually if you like. And it's found 3 instances, one of which is on the 15th of December. And it's just finished. Now that's pretty amazing. You just witnessed a search across over 1.3 petabytes of globally distributed packet data, with it taking just 30 seconds to find all the packets to and from a specific IP address. Okay, let's zoom into the traffic it found on the 15th of December to have a closer look. Actually, I'll download these packets now while it's still zooming in. Let's look at the traffic breakdown according to server IP address. We'll also have a look at the conversations. Let me collapse a couple of these tabs so that we can see everything without needing to scroll. Okay, I can see in the conversations that our PC has been communicating with a number of hosts outside the firewall. That could be evidence of a sophisticated attack involving multiple malicious servers. We can see 23 megabytes exchanged with an 81 dot address, predominantly uploaded, and 7 megabytes exchanged with a 67 dot address, predominantly downloaded. Let's zoom in even further to see if we can establish the sequence of this upload and download. Okay, it's starting to become clearer, but let's zoom in even closer. I see it's just finished downloading the packets. So we can see that the data came down from the 67 dot address before the majority of data went up to the 87 dot address. So that's looking like it's probably the executable being downloaded, followed by the upload using the hypertext post. Let's have a look at the packets by opening them in Wireshark. That's interesting. The very first thing we see is a DNS query for a Windows update server. Then shortly after, that server responds with a status code 302. That's a common way of performing a URL redirection. So I'm wondering if this might be one of those exploits like Flame or Skywiper that spoofs a Windows update server. Well, that's something to look into later. Our immediate priority is to find out what was uploaded. Let's filter for hypertext posts. And there it is, the post to the 81 dot server. Let's follow the hypertext stream to see what's been uploaded. Here it is. We can see a username, password and an Excel file called design patent. So it looks like we have sensitive data being exfiltrated. This PC should be immediately isolated to ensure it doesn't upload anything else while working to remediate the breach. So that brings us to the end. I hope I've left you with an appreciation of the new architecture we've introduced in OSM 6.5 and how it simplifies and accelerates investigations across a fabric of distributed Endace probes. As the demo showed, you can very quickly find packets of interest when searching across many probes and many petabytes of data which might be distributed across the globe. That's a real game changer for productivity of analysts involved in threat hunting. Thanks for watching.